Good morning. My name is Peter Thielmann, and today I'll be presenting the operational review for my Data Science Practicum 1 course. The purpose of this project was to create a predictive model able to not only detect potential fraudulent claims, but to give insight into why these claims may be fraudulent. Today, I will provide an overview of the modeling process along with an outline of the final model and its performance. We will discuss some of the unique machine learning methodologies such as deep feature synthesis for variable creation, ELI5's explain prediction package, and how these methods impact and ultimately improve a claim adjuster's workflow. We will discuss next steps and look to the future regarding implementation, adjuster feedback, and potential improvements to the model. Now, before we begin, let's define what a fraudulent claim is for those who are not familiar with insurance terminology. Fraud occurs when someone knowingly lies to obtain a benefit or advantage to which they're otherwise not entitled. An example of this might be a case in which damages to a vehicle are exaggerated, non-existent, pre-existent, or the vehicle was just damaged at a later point in time. With that in mind, let's jump into the review. First up on the agenda is to look at how we will evaluate the model. The receiver-operator characteristic curve was used to evaluate the predictive power of the model. We can interpret this graph by identifying the separation between the blue and that red line. This shows the model's ability to distinguish between the two classes, which are fraudulent and non-fraudulent. The red line basically shows a random selection or no real predictive power. What we would like to see is a differential between these two lines. The next graph we will be using to evaluate the model is called a lift chart. This chart is built by sorting all the predictions from low to high, then deciling. Each bin defines the average prediction. What we'd like to see here is a very low predictions in bins 0 to 5 and high predictions in bins 6 to 9. The things to identify are an overall upward trend in the graph. Let's take a look at the modeling approach and the data set that was used. We started with 1,000 rows of data and split this into two different data sets, training and validation. A gradient boosting classifier ultimately proved to be the best performing model and selected as the final classifier. We used methods such as outlier removal, target encoding, and feature synthesis to prepare our data for modeling. Automated pipelines, which we will discuss a bit more in detail later, were used to identify the optimal modeling data flow. 38 independent features were in the initial data set, which included things such as age, hobbies, severity, and many more. As mentioned, our target contained binary values, fraudulent and non-fraudulent, and the distribution was not terribly imbalanced. Now, let's dive right in and see how well the model performed. Taking a look at the ROC curve, we can see that the model exhibited excellent predictive power. We have a rapid increase up to the first 20% and great separation between the classes. I was expecting stair-stepping with this model, which sort of looks like small stair steps on the blue line as it increases, but due to the ensemble modeling approach that was taken, it was fairly smooth. The lift chart has a nice upward trend with little volatility, especially in the lower bins. There's a nice sharp rise right after our cutoff, and that identifies that we are correctly separating these predictions. Overall, the model performed very well, and later we can dive a bit deeper on the evaluation topic. I know when I'm listening to a presentation, I'm always just anxious to see how it did and get to the good stuff. So next we'll cover a not so fun but vital improvement that was made to the modeling process, and that involves data extraction and databases. So a mock database server was created in MySQL Workbench. This server provided a place which emulates a sort of real-world scenario data store. Many times a data project can be 70%, 80% data extraction, cleaning, etc., and only 30% or so modeling and evaluation. Now, I don't expect anyone to understand what this code is doing, but I want you to notice how minimal it really is. Normal data extractions and loads can contain thousands of lines of code. connecting to many different data sources. Data scientists or analysts can sometimes be responsible for writing that code. Using this technique, time and code length was kept to a minimum when dealing with this unpleasant but necessary step in the process. What is feature engineering? Basically, we're getting our data ready to model. This sort of goes hand in hand with data cleaning, but here we apply different techniques such as regularization, aggregation, and anything else that we might find useful in the final product. First, we look at each numeric feature and removed outliers. If you look at a normal distribution, you can see that 99.7% of the data is within those first three sections, known as standard deviations. We want to get rid of those other 0.3% since these outlying values may skew how our model predicts. For the categorical features, we use the technique called target encoding. Now, some of these slides are more for documentation, so in 5 years when we look back, we can remember what we did, or if someone is interested in learning more. Most models do not allow for categorical input, meaning we can't enter letters or words. We can just think of target encoding as a method to translate a non-numeric value into a numeric value that we can use for modeling. Deep feature synthesis was used to automatically create new features. More data is better, right? This Python package was quick to set up and use, as well as provided hundreds of useful features to try in the modeling dataset. I kept it pretty simple here, only using additive or multiplicative interactions, but for how easy it was to use, I can see this being used quite a bit in future projects. The next part of the process involved bootstrapping. Again, more data is better, right? Initially, bootstrapping was heavily used to attempt to get a more robust model. Several thousand rows of synthetic data were created and the models looked great. However, training time was an issue when fine-tuning, and ultimately bootstrapping was kept to a minimum to put more emphasis on tuning the model. How did we produce the final product? Magic? Well, sorta. Teapot is an automated pipeline technique that allows the analyst to test tens of thousands of different pipelines. A pipeline is a defined process that the data flows through before it reaches the final classifier. Note, it does not replace the analyst. It just gives the better understanding of what might be needed on a particular data set to optimize the prediction. Dask is also a package that allows the whole process to be run via parallel computing, which separates these tasks and runs them at the same time. And this is a quick visualization of how parallel processing is done in Dask. You can see several different pipelines being tested on different cores of the CPU. Also, it's really colorful and honestly fun to watch it work. The final pipeline consisted of a gradient boosting classifier. This ensemble method consists of several weak decision tree learners and provided a smooth lift. K-best algorithm was used to help narrow down which features were truly important in the prediction. After selection, the pipeline was iteratively trained using a grid search that scanned over and tested many different hyperparameters to optimize the model. Here we can see features that proved to be the most important in detecting fraud. This graph shows which features were the successful ones and how successful they were when compared to the others. The real heroes here seem to be severity and the insured's hobbies. This topic we can always come back to later, but this chart shows the trade-off between precision and recall. Basically, it's the classifier is better at reducing false positives or better at reducing false negatives. The cutoff point can be adjusted in the future if the adjusters are receiving too many claims that are labeled as fraudulent, but really are not. The confusion matrix shows how well it classified each example in the test dataset. The product is excellent at not allowing a lot of fraudulent claims to pass unnoticed, but at the cost of identifying non-fraudulent claims as fraudulent. Next, I'd like to talk about the future of this product and how it impacts the business. As we just mentioned, identifying a non-fraudulent claim as fraudulent may impact the way a customer is handled. It's sort of one of those guilty before innocent mentalities, and we do not ever want to treat a customer unfairly. Remember, this is a predictive model that is never 100% correct. Educating adjusters on how to best utilize this tool will be an essential part of its success. Consider a beta testing phase as well, where a small pilot group is hand-selected to try the product before releasing it to all the adjusters. This will allow feedback and work out any kinks in the workflow. And this product comes with a bonus. Imagine someone hands you a claim and says, "This claim might be fraudulent." Okay, well, why? What should I be looking for? I don't know, but the computer says it might be. Explaining predictions is a new method that was explored with this product. With the use of ELI5, which stands for Explain It Like I'm 5, we can provide adjusters with a bit more information on why we predicted fraud. This at least gives the adjuster a starting point. We can see from the chart on the left what the package provides as important to this particular prediction. In the lower right corner, we can see what a possible message for the adjuster may look like. Working with business systems to provide actionable insights from the product may provide much more value than a simple fraud, no fraud message. As with any new product that is released, feedback is one of the most important things to follow. Is it working? Do they like the product or use it? How does it affect their workflow? These are all some of the key specifics that we will look to gather after we roll out the fraud model. This also gives us more data, and remember, more data is always better, right? I want to thank you all for sticking through the presentation, not falling asleep, and I hope you enjoyed it. For more information or any questions, feel free to leave a comment below or visit the GitHub repository, which is linked in the description below. Thanks.